Hi guys, and welcome to assignment 2 instruction video for cloud native applications. This is part of the module design patterns and architecture. And today we will go through how the concepts from the course literature relate to the practical assignment that you need to implement. If you have missed the instructions and some QA, I have answered it in week 12 vlog. So please have a look there before watching this video. There are also some intro to continuous delivery with GitLab and suggestions of where to start here. Today then we'll dive in here to anatomy of a Kubernetes cluster and how basically which part of it we're going to explore in assignment 2. So Kubernetes cluster is the architecture that underpins the Kubernetes platform, provides orchestration for deploying and managing basically our containerized cloud native applications. Hopefully you already at this point have went through Kubernetes cluster infrastructure exercise. You set up your infrastructure suggestion basically from Matt's scripts, and hopefully that is working. And in your network topology you can see all this nodes. You should have a jump host, a load balancer, and finally control plane nodes and worker nodes. So our control plane is the master node that's responsible for controlling the cluster, managing its state, and orchestrating the workload between the working nodes. It contains a bunch of software that you don't have to go in that much into it and how it works, but if you do, that's that will help you understand a little bit more how it works. So it has a key value store for the cluster data. It has the API server that acts kind of like as a front end and exposes like Kubernetes API. And it has a scheduler, a bunch of basically features that help the cluster function. Then our worker nodes are the machines. We could say that it corresponds to virtual machines that you used to work before on CS Cloud. They have a set of a kubelet, kube proxy, so they are basically where the actual application runs, the actual containers run. There's also where the software for container runtime runs. In this case, in our case, it's Docker. And finally, we have pods, the smallest deployable units in Kubernetes that encapsulates one or more containers. And that's where the scaling happens. So for Taskit and notification services, this is what you're going to be using to the pods is what you're going to be using to scale your microservice. And finally, we have storage, right? So in the requirements of I2 says that storage has to be persistent. So both MongoDB and Redis probably have to have persistent volume claims. So Kubernetes knows where the data needs to be stored and persistent over the, so even if the pods are not running anymore, that your data is saved. So not more complicated than that. We are not doing any database scaling at this point. So to start off then with the A2, after you have completed cluster infrastructure setup, my suggestion is that you proceed to cloning Kubernetes, this WIP repository that you find in the examples, and start with setting up everything locally. So you have your Kubernetes instance running on Minikube on your computer, and you have a full setup with Docker Compose and the scaffold that works in your development environment. So you make sure that once you start making changes, that you test it locally before you push it to your GitLab pipeline onto production to your Kubernetes cluster there. You already get in the example sort of the basic pipeline, and as we talked in the stand-up this week, you can go as as far as you want, but you don't have to automate more than necessary at this point. As in terms of patterns, what you would need to know later at the exam and what you start working with here is the service abstraction pattern. So your first task is basically to understand how Kubernetes natively implements this service abstraction pattern as described in the literature. In this case, anything can be running on a worker node. It can be your taskkit service, it can be a notification service, and then another service will probably run the message broker that you will pick for handling communication between the services. The client application don't know anything about how the service is implemented. So this is like what the service abstraction is basically. You don't need to know what language it's implemented, what framework is running, nothing. You just have an endpoint to access the service. And then through load balancing, you probably you just get an URL or API to access it. So anything can become independent microservice in the Kubernetes infrastructure. Both your database, in this case, and the example, they have MySQL, and for the messaging, they have Kafka. So that's also something to consider. This is basically what we are doing. The infrastructure, the architecture for our assignment 2 was very similar to this one. And then all your scaling in at this point is your taskkit and the notification service. Then what is needed to add to taskkit service? You need to add session management. That basically just one instance of that, but just make sure that it is persistent via mounted volumes. And in this point, you can also add authentication and authorization. Think that if you want it to be integrated with Slack, then maybe this is what you need to use for user handling, if you include it in the messages later. But this is an optional point, although really consider implementing it at this point, because in the group project it is mandatory. For the notification service, it needs to basically communicate with the message queue and the queue messages and send Slack notifications, probably using Slack API and the talk secret token that you have gotten in your repo. A challenge here, which is again optional, this is a pretty small microservice. So it's a great chance to try a different framework, a different language, and really explore basically how to implement the service abstraction with different tools. Then why a message queue? So what you probably used to from the previous courses and from the classical sort of experience with client-server infrastructure is the synchronous communication, so-called request response pattern. So all the APIs that we worked in 1dv027, be it GraphQL or REST, work like this. And in this assignment, then, for the first time, we will be trying asynchronous communication. And this is the simplest case of asynchronous communication. We're implementing a single receiver pattern. Again, this is an illustration from the course literature, where they describe basically placing orders in the system, and in our case, we're placing a task that creates sort of like an order. If we wouldn't use a message broker in a cloud scaling setup, when maybe we receive thousands of orders or tasks in our Taskit app, we would have an array of potential issues. If you have synchronous communication without a broker, the services become tightly coupled, so then the Taskit would have to wait for the notification service to be available. It creates a bottleneck. It will hang. You would have to wait and be blocked by the other service, basically executing the task. Without a broker, it would be challenging to also balance the load because you don't know which one needs to handle what. It creates problems with reliability. You would get basically the services will become tightly integrated, and it will eventually reduce performance and lead to message loss. So this is this is really necessary for larger setups. Then, of course, with the request response pattern, you also can make handling the requests asynchronous. But yeah, the message broker and this pattern is another way of basically handling this task. Yep. So we would have with the message queue, the services become decoupled. They are easier to scale. It increases reliability and persistence of our messages, and eventually also increases efficiency of the whole app that's exposed to the user. So what you need to do in terms of a message queue is that you need to set it up as a microservice in your cluster. So don't use some kind of external message queues. So it needs to be part of your app. Provision it on your cluster and interact with it both from the Taskit service and the notification service. Then it's completely okay to use any type of libraries. Here's a link to basically Hello World example, interacting with RabbitMQ in JavaScript, and there are tons of tools for other languages and frameworks as well. Another alternative that you can consider is Apache Kafka, also open source message queue, and yeah, slightly different basically, but also very, very popular. So yeah, good luck.